Hi everyone, I'm Sirio Belli from University of Bologna.
From the University of Copenhagen.
And I'm Ariel Verli from the Observatory of Padova.
So we organized, we thought a lot about this discussion session, and we put a lot of work in the title slide, as you can see. Actually, Ariel did. So I'm going to explain how it works in a minute, but we made a call. We decided to use one of these websites to try and engage people. So while I tell you what we're going to do, please take your phones or iPads and look at the QR code so you can log in. This is called WooClap. It's used for like engaging students in the classroom and stuff like that, but it's sort of like spreading like wildfire at conferences lately, so we thought we would give it a try. The idea is to try and engage as many people as possible, particularly, you know, younger people who would probably not speak up and say something really controversial, but at least you feel like you're part of this. So we're going through 3 different topics: gas phases, multiscale physics, and star formation histories. For each of these topics, we will have one quick poll using WooClap. We will show a couple of slides, and hopefully we'll have plenty of discussion. So feel free to interrupt us at any point and to tell us all of your most controversial ideas. So if we are ready with this, we can start with the first topic, which is gas phases. We've heard a bit yesterday about how important it is to consider different gas phases. All right, so our first question is, which phases do you work on? You can pick more than one option. Stars, for the purpose of this question, are one of the gas phases. There's also none of the above if you are a theorist who only works with black holes or something. We have one. So, wow, it's like looking at the horse race. Stars are winning. Neutral gas is doing really well. We did not expect that. Ionized gas, molecular gas is not doing so great. So the other fun thing is you can take the total of the numbers for each of these answers and compare that to the total number of people who actually are participating, which is 85. And you can see that I think most people picked more than one answer, or I guess the average is not one. All right, so I think we are converging. So most people have something to do with stars. I'm happy about that, personally. But of course, it's a gas conference, so we have a lot of people working on different gas phases. Ionized, neutral, and molecular, I mean, they're pretty close to each other. That's interesting. And I think it's important also in the context of what we heard about yesterday. I think this is one of the main, I would say, things to keep in mind nowadays. You know, we're supposed to do multi-wavelength astronomy, and the next multi-wavelength is multi-phase, I think. So to start the discussion here, before we get into the science, I think it's interesting to talk more about like us as a community. So are we too compartmentalized? You feel like, you know, you mostly work on one phase, though I don't think that's true. And also, how important is it from the observational point of view to make it so that people who come from a slightly different field can indeed use data from all fields, from all facilities, probing all phases? So I'll give you an example. I do mostly stars and ionized gas, but at some point I realized that molecular gas is indeed very important for understanding star formation. So I started looking into it, and you know, I don't do interferometry. It's like, it's very scary, you know, the UV space and all of that. But for example, ALMA offers data cubes that are very easy to interpret. You know, there is a very nice infrastructure for the archive. I think this is really important moving forward, to try and have the community use all these facilities, all these tools, so that we can, it's much easier to understand what molecular gas is if you can actually access the data, for example, and if you can write proposals without being an expert. So I'll leave it up to you guys now. Any opinions on these, questions or comments? Do we all agree that it's easy to use data from facilities that you've never used before, for example?
Testing, testing. Serra, I'm sorry, I have to disagree. As someone who has been trying to work with our ALMA Science Archive, the setup has been difficult in order to get data. And so I think that's somewhere that we could improve, is that I don't think there are lots of reduced ALMA data cubes that are readily available. You can just grab off the archive. And if you want anything more than a handful of galaxies, it takes hours and hours to look through. And so I think that infrastructure could be improved.
Yeah, I mean, I think it's a matter of points of view. I don't know if you've ever tried to work with KEK data, for example. You will quickly find that the ALMA archive is good, but I agree with it. It could be better, yeah. Other opinions? Here, Ariel?
Yeah, I very much agree. ALMA is difficult, but any other facility is way more difficult. So ALMA made ALMA and all the... Huh? I have data size of 1, so I don't know. Oh yeah, okay. The problem is that, yes, we are compared... that word. But we were way more, let's say, 10 years ago. So ALMA show us, it's a beautiful example of in what direction we can go. And I think that in order to make experiences like ALMA possible, we as a scientist community needs to invest some time also on what was called the technical side. So another example that comes to my mind, in a few years, a lot of new facilities will come online, assisted by adaptive optics, which is, I mean, different from here. But another example where we need to be prepared well in advance to face new technical challenges in order to extract, to get all the beautiful science that will be possible to do that. But we have to invest sometimes in technical aspects in order to be able to be rewarded by this investment. So.
Yeah.
Yeah, I think if you're worried about working with an interferometer, I'd like to tell you about something called the SKA, which is coming. And I think the success of ALMA is the development of the ARC nodes, and I think those are brilliant. And if you have a problem with them, email these people, and their job is to help you. And the infrastructure is possible for the SKA there, but I don't see that the same emphasis that existed in, say, like 2009 and 2010 to build the ARC nodes. I'm not currently seeing that for the SKA as emphatic. And so this is going to be, I think, a thing to start working on now for something that will be developed a few years from now.
Go ahead, yeah.
Yes, so maybe Paula can comment more than me on ALMA or any other European facilities, but as a European, you know, there is a user committee per country, and those people are there to in fact, tell what are your needs, and they tell them to ESO staff members, and probably you know that every year you get a survey asking what are your needs, what you need. So basically for ALMA, if you are not happy, please tell that, and I think ESO people are really glad to do their best to improve the archive and any other thing.
Behind you? Yeah, that's... Can you pass it behind?
Yeah, I mean, yeah, interferometry is absolutely terrifying. I'm saying this as somebody who works with meerkat data. Yeah, but I'd also like to say, like, with the SK, it is still in the very early stages, but with meerkat, there's been a lot of progress being made in trying to make these things more accessible and to get more people to use this amazing telescope and prepare for the SKA. So yeah.
So Greg and then over there.
So I think that making data cubes accessible is great, but there's also a lot of details into getting the data into a usable format for your science goal. So for example, if you're studying some galaxy that has extremely small sizes, or you want to emphasize emission at different scales, then you don't just need a data cube. You need to learn how to, deal with the visibilities and the weighting and the tapering. And so it's not just about making data accessible, but something I think ALMA's been getting good at is providing lots, and NRAO has these like interferometry workshops teaching people about the nuts and bolts of interferometry. It's not just something where you can download a data cube and immediately get the answer you know. So I think there has to be this dual investment in making the data accessible, but also educating especially younger astronomers, but even old goats like me, on how to use these new facilities and understand the relative complexity of the different facilities.
Okay, last comment from over there, yeah.
Yeah, so Ariel told me to have a hot takes. So my take is actually that I don't know that it's always great to have data completely accessible to non-experts. As a simulator, I could have access to data, but there's a lot of kind of hidden complexities, maybe kind of building on what Greg was talking about, that I'm going to miss. And so, you know, the idea of allowing somebody who's a non-expert, or not allowing somebody, but just running as a non-expert with data that you don't actually understand, whether that be simulation data or observational data, can lead to kind of dangerous conclusions. And so I think rather than just making data accessible to non-experts, it's more important that we make kind of ourselves accessible to non-experts in our field of expertise. And so kind of more collaborations is much more important than more data accessibility.
Thank you. This took a really interesting spin. Last comment?
So I actually agree with Stephanie to some extent, but I should not for the purpose of this. So I think that Stephanie's take shows how bad we are at documenting our data, right? Because people should have access to data and understand what has been done to the data without having to know how to do that processing themselves, right? And I just wanted to leave you with one question, which is that the whole thing seemed a bit one-sided, right? So people are talking about ALMA mostly, but I wonder if the radio astronomers have any problem using optical data.
JWST, for example.
JWST, yeah. So.
Yeah, well, we'll leave that question for later maybe, because we need to get to the science. So let's talk about gas phase for another few minutes. Here are just two examples of why it's really important to look at more than one gas phase. So trying to bring also the debate up to high redshift. Ionized gas, for a long time, we've studied rotation curves at high redshifts, redshift 2 and 3, cosmic noon, with oxygen 3 and H alpha emission lines, tracing warm ionized gas. This is from the CHEMOS 3D. On the left, you see that as you go to higher redshift, on the y-axis you see V over sigma. It goes down. It goes from 10 to in the local universe, thin disks, fastly rotating disks, to like 2 or 3 predicted at redshift 5 and 6. Or measured at redshift 2 and 3, V over sigma is around 4. So it's half of what we find in the local universe, or even less. Now, in the last few years, there has been a very interesting development. On the right, it's a beautiful example from Lely et al. With ALMA. At redshift 5, you see a beautiful disk. It's really thin in the sense that V over sigma is like 10. It's just like a local galaxy. So clearly here, there are a lot of things. I don't know if it's a real effect, but clearly it's possible that we are missing part of the picture when we look at just one phase, because maybe the warm phase traces a thicker structure. Another example is about outflows. We've heard a little bit about this constant struggle between the theorists and the observers, where the theorists always want a higher mass loading factors, and the observers try really hard, but it's hard to measure high mass loading factors. But even here, if you look at different phases, you may find surprises. So in the local universe, this is a recent study using the sodium deabsorption line that traces neutral gas. On the y-axis, you have the mass outflow rate from neutral gas, and on the x-axis, you have the ionized mass outflow rate from the same galaxies. And we are talking about 1 to 2 decks in difference. So the neutral phase brings 10 to 100 more mass away from the galaxy. So clearly, here also, if you only focus on the ionized gas, which is typically easier to measure, you're sort of missing half the picture. So, is this really a real effect, particularly this one, or are we talking about different instruments with different resolutions, different techniques, and actually we are mostly biased by observational effects? What do people think?
So about, for example, the plot on the left, maybe, I mean, if you were suggesting that one possibility is that the hotter phase is tracing some thicker component, but looks like, I mean, the phase is hotter also at lower redshift, so maybe it's not just that. Maybe are there observational biases there? I don't know.
Alice?
I need the help of everyone here.
Turn on the microphone, please. Thanks.
There is a combination of two things. Like here, probably there are differences in the different gas phase, but also the observations are different because the resolution, as an example, the spectral resolution here is different, the PSF is different. Also for the outflows, the situation could be different because we are using for the sodium D something that is an absorption, and for the ionized gas, it's an emission. So the techniques to quantify the amount of outflowing material is different. And then, of course, there is the extra effect, the translation of what we observe into the mass that is different in the ionized and the neutral phase. So I think that it's a mix of all of these kind of things. It's not easy. Depends on the cases.
One other difference here is that the sample is different. The type of
Also.
galaxies that are observed with ALMA are different. Over there.
Certainly from the nearby galaxy perspective, different gas phases very clearly show different morphologies and distributions, and to some extent kinematics, but really, I mean, the nearby galaxies show this directly, so I think it shouldn't be too surprising if we find it again at high redshift. Of course, the galaxies are more vigorously star forming, so some of the physics and the dynamics change, but some of the fundamental questions of essentially how the observational biases come into it could easily be tested with nearby galaxy samples.
Okay, great, thank you. We'll move on to the next question.
Okay, yes, you hear me. Okay, we have seen yesterday and today that star formation is, as we all know, is a multi-scale, is regulated by multi-scale physics. So we have different processes that may regulate the conversion of cold gas into stars and what happens after, depending on the scale we look at. So in giant molecular clouds, the physics, the scale of giant molecular clouds, the physics is very different than on galactic scales. So we wanted to ask you this question. So if you agree with this strong sentence, we only need equilibrium between gravity and stellar feedback to regulate star formation. We do not need any other ingredient.
Maybe that was too strong of a wording we chose.
So it seems that, yeah, no, still increasing. Okay, this is a strong result for a strong sentence. Okay, so, well, apparently we do not need, we need something else than the equilibrium between gravity and stellar feedback. So, yeah, is someone willing?
One would like to defend themselves.
Yeah, indeed, is someone willing to elaborate on why they agree?
I think, I mean, as written, it's very strong. So you obviously need accretion of gas or something like that. But there are aspects of the picture that you can isolate out that are quite important, that as written, yes, you only need feedback and gravity to do something like there is a theory that does explain the scale, the thickness of disks and that sort of thing, and all it has in it is feedback and gravity. Is that true? I don't know, but there is a theory that explains it. But if you then go to like Sandro's talk and try to explain all the properties of galaxies and all the regulation that happens to start a little mess of things at redshift 10 and turn it into the Milky Way or whatever, then yeah, you need more stuff. Yeah.
So what is this more stuff? Anyone who disagreed? Yeah, magnetic field. We had a talk about the role of magnetic field in regulating star formation, right?
Yeah, I think the challenge might be to disentangle things that are specific to really the small-scale physics of galaxies that hopefully is very similar across all galaxies at a given, metallicity, for example. So, for example, the IMF and so on, there are probably variations, but at fixed metallicity at a given epoch, you might hope that the IMF is something well behaved. So there's this internal part, and then I think there is this additional, let's say maybe random or stochastic part coming from the environment that is related to merger and how you exactly feed each individual system. And if you're able to disentangle those two things, then we can hopefully learn about really what the different physical contributions are to this, to the star formation and to the equilibrium picture.
Okay.
Of course, I would say that there is the environmental effects, specifically, especially low redshift, although I don't think they regulate the star formation history as a whole. Why I voted I disagree, I was thinking about AGN. At least from the theoretical point of view, there is a very, very strong let's say indication that AGNs are needed to stop the star formation efficiency in large massive galaxies. I'm not sure observationally we have all this evidence. I mean,
yeah, like huge outflows sometimes are not so ubiquitous in the local universe. So this may be, one of the...
I just want to
indeed. What you said, we sometimes do not have this strong evidence from observations. Yeah, but okay. Anyone else?
I guess it's sort of on the surface, but understanding of how feedback operates in this low mass galaxies at high redshift, because many of these equilibrium models, they are formulated for normal star forming galaxies that we see around us today, where nice disks exist, and maybe in this case, dynamical equilibrium picture is applicable, right? But when we go to the slow mass systems at high redshift with very vigorous star formation feedback, it's a completely different situation, right? And our understanding in how outflows are launched and recycled is needed to understand its evolution.
Okay.
The people who disagreed, I think it's worth asking, what do you think? Do you agree that with slightly milder version of this, like that feedback is mostly what regulate star formation, at least in short time scales?
So I think the biggest issue with the sentence is perhaps star formation. What does that mean? Because I think if you're asking somebody, what's regulating star formation inside M20 on small scales, they're not going to consider stellar feedback, right? So it's all, or they might do in a extract, some situation. So I think this question, there's a lot of subtleties in phrasing this, which makes it very difficult to make any strong statements. So, and star formation, based on who you talk to, means very different things. So I think you need to specify what star formation really means in order to end up with a sentence where I can agree with, right? I think that's probably the biggest challenge. So I think this is very much a scale question. What scale are you looking at? what star formation are you considering? Going to a galactic-wide star formation rate, well, then you might end up with a simpler model, and that's what we're finding coming out of Lambda CDM. Going on small scales, it definitely is not like that. Going close to an AGN, we know the star formation rate in the Milky Way center appears to have had a different structure to what we do see in the disk, etc. So there's clearly something that comes in, and that comes in on the local scale. And whether that local scale matters or not, I think is a very interesting question. And clearly there seems to be a transition somewhere around 100 parsec or so spatial resolution where we get a different situation. And so I think that's a very interesting question. What does it matter? When does it matter? And what predictions does it really matter for?
Yeah, very good point.
Yeah, I don't know if we're allowed to ask a question as a comment, another question, but just generalizing what Jarle just said. Equilibrium, remember, it's a new idea. This whole ecosystem thing's only been around a decade or so. It works for the Hubble sequence today. Ultraluminous starbursts even today, they're not in equilibrium. They're disequilibrium, right? And so my question to the experts, there's a frenzy of working on redshift 10-ish galaxies with JWST. What redshift is nothing, is anything you're looking at in equilibrium. And in fact, if you tried to explain things with an equilibrium model, might you go terribly wrong? I don't know the answer to that.
Ask the mirror, right?
Yeah, do you think, but we already addressed this a bit. So what is the main difference, with redshift? So let's move to the other, maybe controversial, maybe not, topic, which is star formation laws, the first talk we had at this conference. So are these star formation laws really multimodal, or is this an artifact? So as Robert said on Monday, we have these three regimes. So one at low density and the other, yes. Thank you. Yeah, one at low density, but there is then the intermediate density regime, and then we have the high density regime, and this is another example of this bimodality of star formation laws. So, well, I don't know if you have strong opinions, if this is reality or some artifact. So, for instance, I can give you my personal opinion. I think that in the low density regime, what we see is actually an effect of projection of the disk thickness. The fact is that the thickness changes a lot in the low density regions in the outskirts of galaxies. So actually this produces a break that is not due to the density threshold for star formation, but to the effect of this projection. So I don't know if you have other opinions about this regime or the others. Please speak up.
You know, I was on your thesis committee, and so I like your proposal. But by invoking a different thickness regime, you've created a new regime. So.
New regime, okay. So complicated. Anything else?
This is just to repeat what Rob said on Monday, and I think in terms of the resolved properties at the high surface density, you know, if you look at the work that Fangs is producing, if you look at the stuff that, well, I think we haven't actually published a paper, but we find a similar thing in Dynamo, is that in terms of it being two sequences versus a sequence with different slope or anything like that, the data quality is not a problem anymore. Our ability to measure star formation rates is not a problem anymore. It just comes down to what you assume for your alpha CO.
Yeah.
because this can, if you look at like work that people like Yvonne Stryker and Daishikan Orianen and Alberto Bellato in his review have done, like the surface density alone can lead to changes in alpha CO. And so that becomes a parameter that changes systematically along your x-axis on that plot. And so then until we get that better, and I don't think that's possible, because if you like dust, that's fine, but there's a whole nother set of assumptions that you're assuming then. And so I think this is just a thing we're just going to have to probably live with, that we're not going to get the answer to it, because there's no mega ALMA coming. There's nothing that's going to change this.
Okay. So maybe we can say that the conversion from gas emission to mass is in some way less uncertain in this regime because it's dominated by atomic gas than in this high density regime dominated by CO. In other words.
I can give you my biased perspective because I was really interested in the low surface density regime of this relation, and there, based on simulations, you can explain it by efficient dispersal of molecular gas by feedback. And then at high surface density regime, there can be qualitative changes, because if you have all of your gas in the galaxy molecular, there is no way to disperse it, so feedback will just slosh molecular gas around without converting them back to ionized or neutral form efficiently. So and this can produce a qualitative difference like this in terms of slopes.
Okay, a lot of questions there.
If I can follow up on that, so we heard again feedback or something like that. I think we can break it down even to more fundamental physics, that is the really property of the parcel of the gas that will form a stars. And this kind of relation, like the break at the low surface densities and the very efficient star formation at high surface densities of gas, can be explained if we believe some analytical approaches and numerical simulations. It boils essentially down to the turbulence in the interstellar medium, where the regime at high surface density of gas is dominated by the supersonic turbulence, whereas in the break you are essentially dominated by subsonic turbulence.
Yeah, just kind of following up on what's already been said, I think it's important to distinguish between what we call artifacts that are physically motivated, like the thickness that you were talking about, so something that we really care about when we're thinking about how to model these galaxies, and artifacts that could be more observationally motivated. And this is a really late comment, but kind of relatedly on the mass outflow rates between the neutral and ionized phases, even in the neutral phase, they found a mass loading factor of around unity, whereas much lower for the ionized phase. So this type of artifact is both observational in the sense that we're tracing different phases, but also physically motivated. Like, we would like to understand why there's a difference between the ionized and neutral phases. And clearly we already understand that to some degree, but I think it's important to distinguish between purely physical and purely observational artifacts, so to speak.
Okay, so thank you. Thank you for your opinions, your feedback, your ideas. And yeah, I think we can move to the next topic.
Okay, so we got many results on star formation histories also in this conference. And I remember the first talk by Rob Kennicott when he mentioned that it's not so easy to get good star formation rates from acidic fitting when you are measuring many bands and getting complexity in your model. So you're measuring many things, not necessarily that will mean that you'll get good star formation rates. And what I thought was, well, that's very cute, because actually we don't get one star formation rate out of acidic fitting, we get the whole history of the object out of it. So also in the spirit of growing complexity, we will now go to a word cloud where you can actually write whatever you want here. And I would like to know what we think that we can learn about star formation from the stellar fossil record. Because we were looking at some talks on very beautiful detailed physics, and then we smash it all together, make stellar population models, and we infer the history, so we get further and further from the physics. So it's there something that we can learn from the physics about it. Let's see what we're getting. I like how the IMF is there. And note that, just to clarify what I mean by the stellar fossil record, is the acidity of the galaxy, so it also includes the effects of dust, for example. Okay. Now, star formation timescale, I see it somewhere there. That's a very interesting one. Okay. And I like that the biggest word is properties. Oh, history. Okay.
History of accretion.
Okay.
History of property.
So,
It's
yes.
AI.
Yes. Okay. Let me, I'm coming here so I can actually look at that. So, this is very unexpected, guys. So I think I can. Let me see how many people answered. 33. Okay. Let's wait for the number to get a little bit up. So I think we can close it maybe. Okay, so the biggest word here is we can yeah, keep it we can close the voting. Okay, so the biggest word here is accretion. That's quite interesting. So you mean accretion of what? Of external objects, of gas? And how do you imagine accretion from the star formation history? No one wants to defend themselves? Now, let me see. So, time. Oh.
So I think it's possible to infer something about the gas accretion history by modeling, but what's much more straightforward is all the stuff people are doing with Gaia and have done prior to Gaia, which is reconstructing the accretion history of the halo based on abundance tagging of stars and kinematic tagging of stars. So you get an exquisite view of the complexity of the accretion history of the halo from looking at streams and populations in the disk.
Yeah, the amount of things that we can do in the Milky Way, it's very impressive, right?
Gas does not appear.
Yeah.
The word gas does not appear.
And do you think that's justified?
No, I mean, if it is gas accretion, there should have been gas on the wall, on the left.
Makes sense. Yes.
I think it was gas accretion.
Mm-hmm. Yeah, quenching, we can probably measure quenching, right? That's a good point. I think that follows into the... Yes, yes, you can put the slides on. Now, going to like what is the more usual case, so measuring star formation histories of galaxies. We saw some examples of post-starburst galaxies in this conference, and I think it's a good test bed to see if these things work, because these galaxies have relatively simple spectra when you think about it. And it's interesting to see that we found like direct or indirect mentions of it from very different systems. So in jellyfish galaxies, they have post-starbursts as remnants, and you see that you have a slight increase in the star formation rate. Same goes to mergers, as was shown by Scott Wilkinson, but and high redshift, basically any quenched galaxy that you can find is post-starburst. So not necessarily as a starburst, it might be a normal galaxy that just shuts down the star formation very rapidly. So this comes to ask obvious question to Scott Wilkinson yesterday, if all post-starburst was a starburst. The answer is not necessarily, right? So this is a good example of one situation where SED fitting works. And we can see pretty well that it works. But the thing is that we use this technique for many things. So this is a very small summary. So similar to what happens in post-starburst, Watson was showing how you can use that to detect time scales of structural changes in galaxies. So detect something that is different from the typical star formation history. And we also seen some very, very nice application by Artemi Campos-Farinha that he actually showed that the gas accretion stops in Green Valley galaxies in very early times. Stefano Zibetti showed some very nice correlations and ways to understand local scaling relations from global properties. And on, for example, the stellar metallicity, that is a parameter that we derive from that. And we also seen what I think is the dream. So look at what people do in the Milky Way that we saw yesterday by Michele Cignoni, and also this dancing around the, dancing around the main sequence that we saw just this morning from Sandro Tachella. So what I want to ask is quite general, but is how can we get closer to the dream? So from what we actually want to have like stochasticity in the star formation history, and what other applications we could do, such as these ones on the top right, that were very creative applications from SED fitting. Do we have any thoughts on that?
Well, I think that, as I mentioned, I think learning the power spectrum or the star formation fluctuations from individual galaxies is very difficult. But I think there are basically two approaches that we can try to develop further. One is like a Lick indices approach, where we basically look at the distribution of equivalent widths versus colors for a wide range of different indicators. Because when you have different fluctuation spectra, you should be able to break fluctuations in star formation with, variations in the dust and the metallicity with these kind of, color diagrams, basically. The other thing one could do is to actually build like a Bayesian hierarchical model, because each individual galaxy has obviously its own star formation history, and some of them are just going under their burst now, some are going on their burst, maybe 100 million years ago. But if you have an ensemble of galaxies where you believe that they have all the same intrinsic variability spectrum, you could, in a hierarchical way, fit for the individual star formation histories, but for the fluctuation spectrum, in a hierarchical way. So, that in an ensemble way. So these are some of the ideas how one could make progress. Yeah.
Very nice idea.
Maybe this joins a bit what Sandro tells. It's true that what we lack is that we are not able to follow the same galaxy over this time scale. So a way could be that we follow indeed a population of galaxies through abundance matching, like the Beruzzi model, and try to pinpoint different time scales for the different halo gas galaxy as a function of different redshifts.
Thank you. And to what extent do we believe the things that we measure from star formation histories? Oh.
I mean, there is a real risk that, in some sense, with a hint of irony, we are over-interpreting the results we get from SED fitting, where the underlying assumption is that the models are a true reflection of the galaxy and its history. And not all of the models necessarily give the same results. And even further to that, different parameterization. Is it parametric history? Is it non-parametric? These won't always give exactly the same results either. I think, in some sense, blindly trusting the results we get from, realistically, at most 30 data points spanning a range maybe of 5 microns is a bit of a gamble. We can certainly trust them, but we have to be careful with over-interpreting the result.
It's a very good one. May I have a show of hands? May I ask how many of you have ever worked with SED fitting, right? Okay. How many of you have ever worked with deriving stellar population models? Yeah, calculating. Sorry? Okay. How many of you have ever worked with stellar population models, like actually making stellar population models? Okay, so you see that's a huge, huge difference, right? So clearly there are lots more people working with fitting galaxies, because it's something very important, than people who are working in actually making the models and actually fixing the problem that Peter was raising.
I think it's actually a bit funny to look back at how it was early on. So when we actually started deriving stellar masses, people in general didn't believe it. So stellar masses were generally viewed as being, a complete fantasy, and what was real was dynamical masses. So if you go back and you look at the mass metallicity relation, the first version of the mass metallicity relation that's really published is one that uses dynamical masses on the x-axis from Garnett. It was a similar story with the mass star formation rate relation, the unfortunately named main sequence. Again, there is a paper by Guzman from '96 that shows the main sequence. And these things go in orbit. So there's some things that we learn over time that actually work, right? And I think it's the same situation with SED fitting now. There's some things that most people have now accepted work, and there are some things that we haven't accepted is working. And I think that's the challenge always with this is to test how well it's doing. We still don't know how well stellar mass estimates really work, because we don't have a ground truth in general where we can count stars in a galaxy that's comparable to the galaxies we have. So ground truths are a bit challenging to do, and I think that's one of the biggest problems with SED fitting.
So, I'm sorry, I'm sure Angela had a great comment, but we have to wrap it up. I think the point that Jarle made is very good food for thought during lunch. So thank you.
Hi, thank you very much. Thank you for having me here. And so yeah, in the next 25 minutes, we're going to move outside of galaxies, and I will try to tell you what I think is the main connection between the multi-phase circumgalactic medium and how galaxies evolve in the universe. So when I'm talking about the circumgalactic medium here, I'm referring to everything that is outside of the galaxy, outside of the ISM, and within the dark matter halo of a galaxy. So we is effectively the interface between the galaxy itself and the external intergalactic medium. And if we think about the processes that might have formed this gas, the first thing that comes to mind is accretion, which has been studied for decades, since the 70s. And from a theoretical point of view, we expect this, in the classical picture, we expect this accretion into the halo to happen in two different modes. So you can have hot mode accretion, in which this gas is, while it accretes, is heated up to the virial temperature of the galaxy, and then it slowly accretes towards the galaxy itself. Or you can have cold accretion, where the gas directly accretes cold to the galaxy itself. And this depends on the radiative cooling, on the cooling time of this gas, which in turn depends on the halo mass of your galaxy. But then later, cosmological hydrodynamic simulations have shown that these two modes can actually happen simultaneously, and so you can have this multi-phase accretion effectively, where you can have cold streams or filaments of gas that actually penetrate through this hotter medium. But then when exactly these two multi-phase accretion happen, and how farther into the halo can these filaments make it, it's hard to still debate it, because it depends on the resolution of the simulations that is still quite low in general in cosmological simulations. And the situation is even more complex, because we know of course that there are outflows. So the gas tends to go to the galaxy, and it feeds the star formation and the central black hole. And then this creates outflows, multi-phase outflows, that then pollute also the CGM with the multi-phase gas and with metals. And so effectively, to understand, this is a very complicated cycle, is what we call the baryon cycle. And to understand the evolution of a galaxy, we need to understand the link of this cycle of baryons with the galaxy itself. And I can think of some of the main questions that I think are fundamental to answer, to understand this link between the CGM and the galaxy itself, which is, for example, we need to understand how much of this accretion, how much of this CGM is actually coming from accretion and feedback, and we need to understand how much gas actually, and how does this gas accrete into the galaxy, how does this accretion take place. And to answer these two questions, is also important to remember that, as I said, this medium is multi-phase. So these whole processes of accretion and outflow create a multi-phase circumgalactic medium, and we can go from the hot circumgalactic medium, which is collisionally ionized with a temperature of about 10 to the 6 or 7 Kelvin, down to the warm circumgalactic medium, which has a temperature of about 10 to the 5 Kelvin, to the cool photoionized circumgalactic medium, which has a temperature of about 10 to the 4 Kelvin, and is supposed to be formed by these clouds that are embedded into the hotter media. And then, of course, we have also neutral and molecular gas, but at lower temperatures, but the vast majority of the CGM in the halo is composed by this ionized gas. And so we need to understand what is the interplay between these different gas phases in order to answer also the other two questions, and so understand what's the connection between the CGM and the galaxy. And during this talk, I will show you how, with the current data and models, we can answer some of these questions, at least for some specific cases, but effectively, in general, these questions remain quite open. So first of all, I wanted to give you a brief overview of what we know from observations of this multi-phase circumgalactic medium. And of course, being multi-phase, we have observations in very different bands, going from X-ray to optical. And the hot circumgalactic medium can be observed, has been observed mainly in X-ray emission and absorption studies. And this is a very recent result from the observations from the Rosetta telescope, where you see the X-ray surface brightness as a function of the distance from the central galaxy for a stacked sample of Milky Way mass galaxies and galaxies with a mass relatively higher than the Milky Way. And you see that we have detections up to large distances from the galaxy itself. And we found these hot coronae, hot circumgalactic medium, around both elliptical and star-forming galaxies. But the mass of this gas is still relatively uncertain, and so we don't know what fraction of the total baryonic budget within the dark matter halo is actually in this hot component. And the kinematics also is quite unknown from observations, given the lower spectral resolution of X-ray observations. And we know that the metallicity looks subsolar, going from 0.1 to maybe 0.3 solar, but it's still uncertain. So what exactly is the origin and what is the connection of this gas with the galaxy is still debated. Then we have the warm circumgalactic medium, which is so temperatures of about 10 to the 5 Kelvin, is mainly observed with the absorption of O6 lines. And the main result that I wanted to point out here from observations is that we find that people have found that there seems to be a dichotomy between star forming and early type elliptical galaxies, with more O6 warm gas that is found around galaxies that are star forming. So there might be a connection with the star formation of the central galaxy, but again, this is not what the connection is not well established. Then we go all the way down to the cool ionized CGM. So here we have temperatures of about 10 to the 4 Kelvin, and besides being observed in winds up to maybe a few kiloparsec above the disk, in general, there's been a boost in the last 10 years thanks to the new IFUs like MUSE or KCWI. And you can see, for example, a very big result is the finding of these ubiquitous Lyman alpha nebulae around quasars, and in some cases also galaxies at high redshift. And in some cases, they extend up to hundreds of kiloparsec from the center. And at low redshift, this medium has been observed. There's been recent observations of this nebulae, magnesium-2, oxygen-2, or oxygen-3, around starburst galaxies. And you see here an example from very recent observation from KCWI, where you see that we can see this emission up to about 30 kiloparsec from the galaxy, from the central galaxy. And there are some cases also around galaxy groups and quasars where they extend even a bit further. These nebulae seem to be extended also a bit further away. But from emission, especially at high redshift, we have still limited sample of galaxies, and when we have emission, when we have detections, we can see the emission, as you can see here, up to maybe a few tens of kiloparsec from the galaxy itself. So that's why the vast majority of the observations are actually of this cool phase are actually in absorption, and these have been observed these gases have been observed in absorption for decades, and around thousands of galaxies of different kinds. And the idea here is that is to use these galaxy quasar pairs, so samples of different galaxy quasar pair. So you have a line of sight that goes with which you observe the background light of a quasar, and then looking at the UV and optical absorption lines in this spectrum, you can characterize the medium, the circumgalactic medium of the galaxy in the foreground. And with this kind of observation, we have observed the circumgalactic medium around many galaxies and up to the virial radius of a galaxy and beyond. And the downside of this type of observations is that you only have typically one line of sight per galaxy, so you don't have a clear idea of what is the structure of the CGM that you could have from emission, but you can have large statistical sample. And also you have a high, in many of these observations, you have a high spectral resolution, so you can see the same. And what we have found is that you can study the kinematics of this gas, and what people have found is that you can see the same transition at different velocities, meaning that this gas is probably composed by different clouds that are moving in the halos of galaxies, and these clouds seem to be bound to the galaxies themselves. Then people have looked at the metallicities of these absorbers and for different galaxies, and they find that this metallicity is has a quite wide range for different absorbers. So some of these gas may be coming from external accretion, some may be coming from supernova explosions, from outflows from the galaxy, and this is also still quite complex. And the last result that I wanted to mention for this type of observation is the fact that a large amount of cool gas is found both around early types, so quiescent galaxies, and star-forming galaxies. So what you see here is the amount so this is a survey where each point is a galaxy quasar pair, and the same amount of H1 is found both around early type, so quiescent and star-forming galaxies. And H1 in this case is only a tracer, but most of this gas is actually ionized. But this is interesting, is an interesting puzzle, because you need to explain why there is so much cool gas around galaxies that are actually not forming stars. So the origin in general and the connection of this gas also with the galaxy is not clear. So from all these observations, what you want to do then is to try to understand the circumgalactic medium, to interpret these observations through different theoretical models, and And you can do this in different ways. I can think of semi-analytical or analytical models and hydrodynamical simulations. So first I want to focus on the semi-analytical models, and there's many of these type of works, especially in the last maybe 10 years, where you can try to model using some physical assumptions. You can model one or different phases of the circumgalactic medium, and then the power of this kind of models is that they're very flexible, and so in this way you can compare them directly with the data, and you can try to infer some very important physical properties of this medium. And there's many work, and this is a very incomplete list of these kind of works. So in this case, I will, for this talk, I will just want to focus on what I have done regarding this. And these are semi-analytical models that I developed during my PhD together with Filippo Fraternali and Gabriele Pezzulli. And what we have is that we describe the circumgalactic medium as a two-phase medium. So you have these cool clouds that are in pressure at 10 to the 4 Kelvin, that are in pressure equilibrium with a hotter CGM that we call corona. And the hot CGM has properties that are in agreement with the observations that I was showing you before. And then we assume two different scenarios, one in which these clouds are ejected from the galaxy itself due to supernova feedback, and one in which they are actually accreting towards the galaxy due to cosmological accretion, as part of the cosmological accretion of gas into the halo. Then the idea is that you can, what we did is to extract synthetic observations, and then you can get the kinematics and the densities of these clouds, and you can compare them directly with the observations in absorption that I was talking about before. And we did this through a Bayesian analysis for different samples, and then you can infer some physical properties of this gas and its connection with the galaxy itself. So the first paper I wanted to mention is a paper in which we tried to indeed answer the question that I was raising before of why is there so much cool gas around quiescent galaxies. And for this, we looked at a sample of 16 early-type galaxies for which we have observation in absorption of this cool gas. And here they found they found what is the kinematics of the clouds, of these cool circumgalactic clouds around this sample of early-type galaxies at low redshift. And so that's what you see here in orange, and in blue is how we reproduce with our model these kinematics. And what we found is that these are models of accretion. So we found a model of accretion of cool clouds that can actually explain the observations quite well, the observed kinematics quite well. And most importantly, what we found is that these clouds, in order to reproduce the observations, need to be destroyed by the interactions with the hot medium. So they are actually, while they fall down, they interact with the hot gas, and they never reach the galaxy because they're first destroyed by the interactions with the hotter phase. And so this explains actually why you're not feeding the star formation of the galaxy, and explains how can these galaxies remain quiescent with such a large amount of cool gas around them. And then in this other paper, which is the third of this series, we actually try to understand how much of the circumgalactic medium of the cool CGM is formed by accretion or feedback around star-forming galaxies. And for these, we use a very special case, which is the case of the Andromeda galaxy, for which the cool circumgalactic medium has been observed extensively in the last year in this survey. And the power of this kind of observations is that these are in absorption, but being the Andromeda galaxy very close to us, so the Andromeda galaxy is here, we have many quasar lines of sight, and so that span the entirety of the halo of this galaxy. And so for each line of sight, we can extract what are the velocities of the clouds and their column densities. So what we did is that we tried to reproduce this data with our models. And what we tried first was a model in which all these clouds are produced by supernova feedback, so they're coming out from outflows from the center. And we found that these type of models are actually unphysical, because in order to explain all this cool gas with clouds ejected from the center, you need extremely high supernova efficiency to get these clouds out there. So the supernova efficiency is effectively the efficiency in which the supernovae are transferring energy into kinetic energy for this wind to push the clouds up. And in order to reproduce this data, the efficiency needs to be of the order of 700%, meaning that these winds need 7 times the amount of energy that is available from the supernovae. So what we said is that, okay, this scenario is probably unphysical. We cannot reproduce all this stuff with outflows. And we looked at, instead of at accretion models, and in this case we found a very well, so these are the results of the Bayesian analysis. And we found that there is a very well constrained class of models that can reproduce the observations with accretion of clouds. And without going into the details of all the parameters, the only thing I wanted to mention is that we find that to reproduce the observation, we need a low metallicity consistent with accretion from the intergalactic medium. So this whole picture is a self-consistent model in which we can explain all these observations with accretion of low metallicity gas from the IGM. And so the takeaway point from all this is that we can use these kind of models, comparing them with data, to understand the CGM and its connection to the galaxy. Now, after having talked about this, I wanted to move to the second way in which we can actually study and understand the CGM, which is using, of course, hydrodynamical simulation. And now with this type of works, the keyword here, I think, is resolution. And so there's been many works in the last year where you take halos from cosmological simulation and you re-simulate them with a higher resolution, zooming in on them to try to really see, to try to zoom in on the circumgalactic medium and on the galaxy itself. And so what you see here is from the Gibbel, very recent Gibbel simulations, and you have the resolution of TNG on the bottom, on the top left, sorry. And then the resolution increases going clockwise, and you see that the more you increase the resolution, the more you see structures in the CGM. So a high resolution and a resolution that is high enough is really fundamental to see all these flows of circumgalactic medium and to understand how the CGM relates to the galaxy. But then the question is this resolution enough to actually trace all the interaction between the gas phases, between the different gas phases that are really important to understand the CGM? Well, the answer to this is debatable, but I think that it's probably not enough in these simulations. And we can see that here in this cartoon. So this is a cartoon from a very recent review on simulations of the CGM. And you see that the circumgalactic medium is a very multi-scale, like the interstellar medium is a very multi-scale problem. And so we have physical processes that are happening on the scale of the entire halo, but we also have physical processes that happen on scales of 100 parsec or 1 parsec, which is smaller scales than the current resolution of these zoom-in simulations. So to study these interactions, we need higher resolution simulations, and these of course have been done, but if you want a higher resolution, say a parsec scale resolution, then you need to focus on a very small part of the galactic halo. So you see here a list that is not complete of this kind of works. These have been done for different, you can decide which process you want to study, and so you can focus, for example, on a patch of the galactic disk to study the outflow and resolve actually the supernova feedback. And we have seen some examples actually yesterday. You can study the accretion looking at idealized filaments, and you can study the single cool circumgalactic clouds and how do they interact actually with the hotter medium. And I wanted to focus on one example of these last type of simulations. And these are clouds that are actually ejected from supernova feedback. These are galactic fountain clouds. They get ejected from the galaxy itself, so they are at a few kiloparsec above the galaxy. And you see how these clouds, in this simulation, the more the cloud evolves, the more actually it increases the amount of cool gas in it, and this is because it's inducing the cooling of the hotter surrounding medium. And you see that also here, this is the amount of cool gas as a function of time, how this cool gas is actually increasing. And why is this happening? Well, this is happening because we are actually tracing the mixing, we're actually really tracing the mixing between the hot and the cool phase. And if you look at this plot, which is the cooling function from a different set of simulations, but the idea is the same. If you look at the cooling function, so this is the net cooling rate as a function of the temperature, and you see that the peak of this cooling function is actually at about 10 to the 5 Kelvin, this warm gas, mixed gas that is actually, that can cool actually very rapidly. So if you have, so at the interface between the cool and the hot material, you have these instabilities that form this mixed gas at this temperature that can cool very rapidly and increase the amount of cool gas. And also these rates, as you can see, depend on the density and the metallicity of the gas. So a denser and more metal-rich gas can actually cool even faster. And this result is important because if you have this is a clear example of positive feedback, because you can increase with these clouds the amount of cool gas, and there's this additional cool gas can then accrete into the galaxy and feed the star, regulate the star formation of the galaxy itself. But what's important here is that the high resolution is actually crucial here to capture the mixing, so to capture the mixing between the different phases, and so to see this effect, otherwise you will miss it at all. And another case that I wanted to mention where the resolution, to understand why the resolution is important, is by looking at this work that we have published last year, where we looked at clouds that are falling in the halos of Milky Way and M31-like galaxies. And these are actually simulations whose initial conditions are based on our semi-analytical models. And so in the simulation, you see we're just simulating a box of the CGM, and you can look at the inflow of a cloud starting from the virial radius and going down towards the galactic disk. And you see that the more it evolves, we take into account different physical effects. But the main point is that the cloud actually gets destroyed by the interactions with this gas. And you see this here a bit more quantitatively. So we have these are temperature snapshot, and you see that at about 2 giga-year, the cloud is completely evaporated. This is the normalized amount of cool gas as a function of the normalized distance with the virial radius from the disk. And for 3 different simulations, you see that at about half of the virial radius, the cool gas is completely evaporated. And this is consistent. I know that before I showed you that the cool gas, these interactions can actually increase the amount of cool gas. But in this case, remember that we are at very large distances from the disk, so the densities of the gas are much lower, and the cooling rate is therefore lower, and the longer cooling rate means that this mixed gas doesn't have time to cool down, and the final effect is that these clouds are actually destroyed. But even for the destruction, the high resolution is extremely important. This is the same simulation. Now you're looking at the cloud from the bottom up, and the same simulation at low resolution, where the low resolution is still at least 3-4 times higher than what we have in zooming simulation, and the high resolution. So you see with the high resolution, you see better the fragmentation of the cloud, and the cloud actually disappears much faster. And it shows here in this plot, this is the same as before for 3 different resolutions. So the lower the resolution, the more you're artificially increasing the survival time of this medium. And so we need to be careful when we look at the survival time of cool gas in zoom-in simulations, for example. So the resolution is important. And to conclude this part, I would just want to put a general picture of what we find from the semi-analytical model and these kind of simulations. So you have all this amount of IGM clouds that are coming from accretion from the IGM that don't make it to the central galaxy because, so this is for a Milky Way-like galaxy. And these clouds get destroyed by the interaction with the hot gas. But then we also know that to sustain the star formation of this galaxy, we do need accretion from the surrounding CGM. So then the question is, how does this accretion take place? And well, there can be different answers. So one answer is that some of the IGM actually makes it to the galaxy if you have a much more massive cloud or a filament that gets in. And then another solution is that the gas towards the center, the hot gas, close to the Milky Way, to this galaxy, actually has higher temperature, so it can higher density, so it can spontaneously cool and accrete onto the galaxy itself. You can have this induced accretion from galactic fountain, which is what I was telling you before, that we see in simulations and also is consistent with many observations. And then, of course, well, here you know that you can have also stripping from satellite galaxy, and so this gas that gets stripped, this cold gas that gets stripped, can then maybe make it to the center of the galaxy and accrete into the galaxy itself. So what is actually the mode of accretion that is happening in this type of galaxy is still not clear, but it might be a combination also of all these effects. And now to conclude, I just wanted to put here back the same questions that I had at the beginning, which I think remain effectively open questions. And during the talk, I've showed you how we can answer some partly these questions for some specific cases with the current data and models, but still most of these remains unknown. But the future is bright because we'll have many more observations in the next 10 years or so, both in X-ray going down to the optical wavelength, and this will help us to have a better idea of what is the morphology, the kinematics of these, all the phases effectively of the ionized CGM. And also, of course, we need to improve our theoretical models, both from the semi-analytical side to interpret all these observations, and also for hydrodynamical simulations. So despite the fact that the resolution is increasing more and more in cosmological simulations, there are also many works recently on creating subgrid models for the circumgalactic medium implement in cosmological simulation, where you can really trace on a subgrid level the interactions based on physical principle between the different gas phases. And this is just an example for an outflow, for large scale outflows, where these subgrid models are included. And that's it. I just wanted to mention and thank Gabriele Pezzulli, that was originally supposed to give this talk. So I took his place. He couldn't come to the conference. So thanks to him, thanks to the organizer. It was a pleasure. And thank you, everybody.
So I think you have completely forgotten a very important component of the CGM, which is the very cool one. The very cool one.
Yeah.
I mean, we have evidence now from many let's say sub-millimeter observations that there are indeed a lot of cool halos around galaxies from C+, CO, and so I think this is very important. You should not forget it in your simulations.
Yeah, sure. No, I mean, you should take into account of all the phases. I think that the ion, in general, if you consider the whole budget within the virial radius, the ionized phases are more abundant with respect to the cool gas. We don't know really. Yeah, we don't know. But in this kind of stuff, yeah, it might be. But certainly, when you go closer and closer to the galaxy, you need to take into account also of the neutral and molecular phase. Yeah, I agree.
The circumgalactic absorption on quasar studies that you have mentioned at the beginning, including Martin, Hall, Boucher, and others, have shown that in these cases, the circumgalactic medium is accreting, is co-rotating, coplanar, and co-rotating with the disk, and the accretion appears to be, in fact, coplanar and co-rotating on a different. So this is I would say, substantially different scenario from the kind of spherically symmetric accretion that you have expanded in your presentation. What's wrong with the scenario of a coplanar and co-rotating accretion being dominant for the evolution of disk galaxies?
Yeah, so we don't know whether it happens in one way or another. It's true. Like, okay, for sure my spherical accretion is it's an idealized version of how this accretion takes place. Some of these works that I put there and that you mentioned, in the case of the Boucher paper, for example, they are saying that this is accretion based on one line of sight, so an observation from one line of sight. So there are others, there are others, but I think in general the evidence of how whether this accretion is coplanar or not is not really a strong evidence of how this accretion is actually happening just from observations. I think, yeah, there are limitations with observations, but yeah.
The existing observations coherently indicate coplanar and co-rotating accretion. They are few, but there are no contradictions.
Well, there are some observations in which you see, in Andromeda Galaxy you see everything, you don't have it here. But in M31 you see observations everywhere around the disk, so it's not very clear that the accretion there is coplanar.
So from H1 there is the same evidence for many galaxies that the gas that's coming in seems to be co-rotating with the disk. I think the observational evidence is actually quite good.
Yeah, I mean, yeah, the results on this simulation, like what I was showing before about the clouds, for example, being destroyed. I mean, this, however, is so there might be. So I am not saying that there is no rotation at all. So there is definitely a rotational motion. And also in my models now, I simplified everything here, but the things are rotating as well. It's not just an isotropic accretion. So everything rotates with the galaxy. It's just not coming from the plane of the disk, which, well, is debatable, of course, but we don't know.
Hi, so sorry, a quick question, maybe more naive. Hi, right here. Sorry. You mentioned satellite accretion there at the end for Milky Way analogs. I was curious if you could mention that for like M31 analog, considering we know so much about like the satellite population of Andromeda.
Yeah, sorry, could you repeat that, please? I didn't get the question.
You talk about like satellite accretion for like M31 analogs as well as Milky Way.
Mm-hmm.
I'm just curious, that was mentioned in the last slide about the Milky Way analogs. I don't, unless I missed it, was it not mentioned, or for considering things like M31?
You're talking about the satellite accretion in M31? Yeah. I mean, what I'm saying is like we don't really know where this is coming from, but it could come. There are satellites where they could have lost their gas, and this gas is actually accreting in the in M31, for example, as well. Yeah.
I want to give a brief comment. This afternoon, I will show solid evidence that at least down to several times 10 to 17, the H1 indeed distributed in a very flat and thin disk.
That the H1 is distributed, sorry?
In a very flat and thin disk.
Yeah, okay.
Thickness of KPC, 1 KPC.
Okay, well, all these observations, if you saw the H1 column density there, we're going to even lower column density. So it might, we're talking about even larger scales here, for the CGM. But then how does accretion close to the galaxy take place? Yeah, it's debated. I get it. To half the virial radius, yeah, okay. Well.
Okay, so the goal of this talk is to review what H1 observations tell us about the physical processes in galaxies. So it's a very broad topic, so I'll try to cover as much of it as possible, but I'll necessarily have to leave a few things out. Now, we know that galaxy evolution is to a large extent the tale of how galaxies get and lose gas and how efficiently they convert it into new stars or accrete it onto a central supermassive black hole. Mapping the flows of gas of all phases is therefore very important, and this includes the neutral gas. Now, the main component of the neutral gas is indeed hydrogen atoms on the ground state, or H1, and that's essentially everything that this talk is about. Now, the most direct way of observing H1 is through this 21 centimeter spectral line, which is related to the hyperfine structure of the ground state of the hydrogen atom. There are many solutions to the problem of detecting the 21 centimeter line, depending on whether your priority is sensitivity or field of view or what angular scale you're interested in. And I'll skip all these beautiful technical details to just say that essentially we can, with these telescopes, map the intensity of the 21 centimeter line, both in emission and absorption, over very large fields of view as a function, of course, of position on the sky and velocity along the line of sight, over fields of view that can relatively easily reach the 10 square degree mark, but can be actually pushed with these beautiful telescopes up to hundreds or even thousands of square degrees, and with angular resolutions down to better than 10 arc seconds, and velocity resolutions that you can push down to a fraction of a kilometer per second. Okay, so these are really impressive data sets that, of course, are teaching us a lot of lessons about galaxies. Now, some of the key lessons come actually from our own Milky Way, and these are lessons that I think we should always keep in mind when interpreting the observation of H1 in external galaxies. Here you see a picture of the all-sky distribution of H1 in the Milky Way coming from the H1/4π survey. You can obviously recognize the Milky Way disk, the Magellanic clouds, towards the bottom right, but also this abundant extraplanar gas that we find at essentially all latitudes. And now these H1 properties of the Milky Way have been reviewed by many authors over the last couple of decades. I'll mention just a few highlights from this work. Now, one key question is what are the physical properties of the H1? So what kind of gas are we looking at when we observe H1 in the Milky Way or also in external galaxies? Now, very careful analysis of both emission and absorption H1 spectra, like the ones you see on this slide, tell us that in line with theoretical expectations, actually, the H1 is mostly composed of two stable phases. On one hand, we have a warm H1 phase, which is very diffuse and ubiquitous in the Milky Way. It has temperatures of the order of a few thousand Kelvin and thermal velocity dispersions between 10 and 20 kilometers per second. But then you also have a much colder phase called H1, which is very dense and filamentary. The temperatures are about 20 to 200 Kelvin and thermal velocity dispersions between 1 and 2 kilometers per second, which is why you need high velocity resolutions for some observations. Now the warm H1 is optically thin and it dominates the H1 emission spectra. It amounts to about 50% of the total H1 mass with large variations depending on regions where you're looking at in the Milky Way, but also from galaxy to galaxy. The cold H1 is a lot harder to detect in emission because essentially you have these very thin and faint emission lines that are swamped by the bright and broad lines of the warm H1. But actually the cold H1, because it's very dense, it dominates the signal in absorption. And so the combination of absorption and emission spectra is really critical to study the properties of these two phases. And this is something that has been done to great effect in the Milky Way, but it's harder to do in external galaxies because of the lower signal-to-noise ratio, but also because of the limited number of sight lengths where you can detect absorption. Now, Kalber and Houd used the H1/4π data that I showed earlier to do multi-component decomposition of the emission line spectra of H1 in the Milky Way, and then they used this decomposition to create maps of the different phases of H1 on the sky and in velocity. And here you see as an example the distribution of warm H1 in the Milky Way at a velocity of 0 kilometers per second, which is very diffuse, as I said earlier, found everywhere, and very different from the distribution of the cold H1. The difference is really quite dramatic, and we should keep this in mind when we look at external galaxies where we don't have this level of detail. The cold H1 is thought to be arranged along filaments, and these are attracting much attention because they can teach us something about how star formation happens, but also about how feedback shapes the structure of the interstellar medium. Here are recent results that are quite interesting that show that very often these cold H1 filaments are aligned with the magnetic fields in the ISM. And this alignment disappears when you look at the warm H1. It really only holds for the cold ISM. And the idea here is that either the magnetic fields are important to set the structure of the cold interstellar medium, or alternatively, the kind of dynamical events that shape the ISM also have the effect of enhancing the magnetic field. Now, one last result I would like to show about the Milky Way is this one, where you see the fraction of H1 that is in the cold phase as a function of optical extinction. And here the color is coding the volume density of the ISM. And you see that essentially the cold H1 becomes the dominant component at high extinction and at high volume densities, which really strengthens this idea that this cold H1 component, which is a small component of all the H1 mass we're detecting galaxies, is the one that is very strongly related to star formation. Unlike the warm H1, cold H1 traces the regions where you have more shielding, more cooling, and so more formation of stars and of molecules. And these results are very important to then interpret in a correct way the scaling relations between the neutral gas content of galaxies and other key properties. And these have been reviewed recently by Santonge and Catinella for galaxies in the nearby universe. Here you see the scaling between the neutral gas and the star formation rate. The top panel shows the H1 mass normalized to the stellar mass as a function of the star formation rate, also normalized to the stellar mass. And the bottom panel is the same, but for molecular gas instead of H1. And this is all for galaxies above a stellar mass of 10 to the 9 solar masses. And so the difference between the two panels is is very clear. The relation with star formation rate is a lot stronger for the molecular gas than for the H1. But now, armed with the knowledge of what I've told you about the Milky Way, we can understand this, because the H1 mass is dominated basically by this warm H1 phase, which is only loosely related to the star formation process. Star formation is much more strongly related to the cold H1, which however only contributes to about 30% of the H1 mass on this vertical axis, with large variations from galaxies to galaxy. And that's why you've got this very long, very large scatter here. If you compare the two plots, another thing you'll see by comparing the vertical level is that the mass budget of the neutral ISM is dominated by H1. There is a lot more H1 than H2 in star-forming galaxies. The H1 to H2 ratio is typically between 4 and 10 or so. So even though molecular gas is the phase most strongly related to star formation, H1 is providing a huge amount of gas that can in principle keep galaxies going for a long period of time. And actually you see this even better on this slide where I'm showing the depletion time of the neutral gas, both the molecular gas on the left-hand side and the H1 on the right-hand side. And you see that molecular gas at the current levels of star formation rate in the nearby universe is depleted very quickly. For star-forming galaxies, the depletion time is less than a giga-year typically. While the H1 is this reservoir that can sit around for a very long period of time. It's slowly evolving and it can provide material for star formation for long. And so a corollary of this is that any process that can actually affect this large reservoir of gas has in principle the ability of affecting the very long-term evolution of galaxies quite clearly. And so let's look in the next couple of slides of some of these processes that can actually change the H1 distribution and content of galaxies. Now, one area where H1 observations have allowed key breakthroughs is the study of the cycle of gas from the star-forming disk of galaxies up to the surrounding environment and back onto the disk, the galactic fountain. Here you see a galaxy from a star-forming galaxy, the optical image and H1 contours showing in black. If you take the major axis of this galaxy, you can draw an H1 position velocity diagram, which you see here on the right. That is basically the intensity of the 21 centimeter line as a function of position along that axis on the x-axis and velocity along the line of sight on the y-axis. And on this diagram, the rotation curve of the galaxy is represented by these orange squares, and you see that most of the H1 is actually following the rotation pattern. But when you go very deep with very sensitive H1 observations, you also find this excess of faint, very diffuse gas at lower velocities. Now, the interpretation of this is that when you look at an inclined galaxy, you've got a sight line that pierces through, of course, the thin, bright H1 disk, but also this thick layer of gas, extraplanar gas that is shown in green here, that is above the plane of the disk. And this extraplanar gas is to first order rotating together with the disk, but actually does so with a slightly lower velocity. And that creates this extended wing of slowly rotating gas in the H1 line profiles, or equivalently this excess of slowly rotating gas in the position velocity diagrams. And that's very important. These kinematical lags are fantastic because they allow us to identify gas that is above the plane in external galaxies, and then we can study how this gas circulate in the galactic fountain. And this has allowed, as I said, key insights. One of them is that this kinematical lag, which is typically of the order of 10 kilometers per second per kiloparsec, is actually stronger than you would expect. Here you see the rotation curve in the mid-plane of one particular star-forming galaxy. That's the dotted line. The red line is the expected rotation curve at a height of 4 kiloparsec above the disk. And this is below the dotted line just because of conservation of angular momentum as the gas moves up and then back down. And the black circles here are the observations. And you see there is an excess kinematical lag. So the gas is being slowing down actually more than you would expect. And the interpretation here is that this is because of an interaction between gas that is coming up from the disk and the low angular momentum gas in the hot corona around the galaxy. On the right-hand side, you see another interesting result, which is that this extraplanar H1 we detect at 21 centimeter is actually systematically moving back onto the disk, both radially and in velocity, and vertically. And the amplitude of these inflows is of the order of 30 kilometers per second. That actually not only from external galaxies, but you see also the Milky Way here. So the H1 observations allow us to trace gas that is basically on its way back onto the disk in the galactic fountain cycle, while gas that is on its way up, moving up, is not detected at 21 centimeters, most likely because it's largely ionized. Now, another interesting result that was actually already mentioned in the previous talk is that when you try to model all of this, you see that this inflowing gas that you see on the right-hand side is actually including a low metallicity component of gas that used to be in the hot corona and is cooled as a consequence of the interaction between the gas being shot up from the disk and the hot corona gas indeed. And this accretion of gas from the hot corona results in a net accretion of gas onto the disk, which happens to be of the order of the star formation rate. So through the galactic fountain, you're actually bringing more cold gas onto the disk, and this is an important channel to keep galaxies going for a long time. Now, H1 observations allow us to trace other kinds of gas accretion, cold gas accretion onto the disk of star-forming galaxies as well. One of them is the accretion of small gas-rich satellites, and you see here two maps, two channels from an H1 data cube, and that's from a review by Sanchisi and collaborators, where you see a clear connection between H1 in the disk of this large galaxy and H1 in this small satellite. When you run through the numbers of, however, of samples of galaxies, you find that this kind of accretion is a lot less important than the one I've just talked about through the galactic fountain. You typically find accretion rates of the order of 10 to 20% of the star formation rate of galaxies. So this happens, but doesn't seem as important for star-forming galaxies as the galactic fountain. Now, tidal interactions can also do other important things. Here, for example, you see very deep observations done with the FAST telescope showing large envelopes and thick disks of H1 around tidally interacting galaxies. And on the left-hand side, you see one example of such observations. On the right-hand side, you see that the fraction of this very diffuse H1 seems to increase with the strength of the tidal interaction. And Jing Wang and collaborators are suggesting that this might be suggesting that the tidal interactions themselves are triggering cooling of gas from the CGM onto the interacting galaxies. And I think she'll talk more about this result. But we know that tidal interactions can also remove gas from galaxies. We see two clear examples here. On the left-hand side, Higgs and compact group 44, where we detect a 300 kiloparsec long tail of H1 connecting smoothly in velocity and spatially to a tidally disturbed galaxy in this group. And the idea here is that the galaxy lost up to a third of its H1 mass over the course of about a giga-year because of an interaction with the tidal field of the galaxy group as a whole. On the right-hand side, you see another beautiful and famous case, the Leo ring, which is this ring of H1 surrounding a galaxy group. In the work by Michel Dansac and collaborators, the idea is that this ring has formed because of a head-on collision between two galaxies in the group, and is formed of gas that used to be in one of the two galaxies and is now expanding in the intragroup medium. Now, H1 observations were also very important to study the process of gas removal from galaxies in even denser environments, in galaxy clusters. Observations done with single dishes showed that galaxies at low cluster centering radii, so on the left of this plot, towards the center of clusters, have very high H1 deficiency, so they are missing a lot of H1 compared to what you'd expect. And interferometric observations later showed why this H1 deficiency happens, and it's because the H1 disk is getting truncated. You see here a case of an H1 disk shown in white contours truncated well within the stellar body, which is seldom observed outside clusters. And even deeper observations showed how this truncation happens, and it's because you're pulling gas out of the stellar body of galaxies through, because in this case of an interaction, the hydrodynamic interaction between the ISM and the intracluster medium that the galaxy is moving through. And Luca Cortese will talk about all the details of this, so I won't mention anything more except two very quick and relatively shallow points. One is that we are now in a really exciting age where we can fairly routinely map entire galaxy clusters in H1. You see here the example of Hydra observed as part of Wallaby, and the Virgo cluster observed with the VLA as part of the VIVA survey, but now being mapped again fully with Meerkat. And another point is that not only we're getting more statistics, but we're also getting really fantastic details about this stripping process that is allowing us to refine our understanding of how this happens. And this is from our own work in the Fornax cluster. You see here on the right-hand side the position velocity diagram again of H1 along this very long H1 tail, you see a very regular velocity gradient, which is consistent with run pressure within fornax, given the motion of this galaxy through the intracluster medium. So that is a run pressure, a tail shape at run pressure, but very close to the base of the tail. At the start of it, this velocity gradient changes sign abruptly, which means that the tail didn't start because of run pressure. And I think our idea here is that in small clusters like fornax, you have very frequently other types of interactions, like tidal interactions, first acting on galaxies and then facilitating later on further hydrodynamical stripping of gas. Now, H1 observations have also been very important to study feeding and feedback of AGN. In particular, H1 in absorption allows us to probe the very central region around the AGN, parsec scale, where you can look at gas disks or in falling clouds. But what I'd like to highlight here is this very broad wing of blue shifted H1 in this H1 absorption spectrum. So this is gas between us and the AGN, moving very fast towards us at 1,000 kilometers per second or so. And so it's very clearly an outflow of neutral gas, which is thought to be entrained in a cocoon, an expanding cocoon inflated by the AGN activity. And an interesting research thread is actually to combine these studies in the central region of AGNs with mapping the distribution of cold H1 in the environment around AGNs. Here you see the case of fornax A with these clouds and tails and streams of H1 all around this AGN host caused by the interaction between fornax A itself and the galaxies around it. Now, all these processes are doing important things to the H1 content of galaxies, but I said at the start that H1 is not quite strongly related to the star formation activity in galaxies, so does it even matter? And here you see that it does actually in terms of demographic. For example, the offset from the star formation rate stellar mass relation on the x-axis here for normal star-forming galaxies correlates with the offset from a typical H1 mass stellar mass relation. And so this is telling you that if you have a little bit more H1 than you are expected to, you're also forming stars at a slightly higher rate. If you have less H1 than you should, you're also forming stars at a slightly lower rate. And this is less trivial than it might sound because, as I said, H1 is not really very strongly related to the star formation in galaxies. H1 can illuminate also other interesting regions of this particular plot. For example, towards the left and the top left, you have H1-rich galaxies that have very low star formation activity. And this includes, for example, quiescent ellipticals and lenticulars surrounded by these giant disks of H1. These disks have very low Coulomb density, so they're not forming many stars at all. And they're very often kinematically misaligned with respect to the angular momentum of the stellar body of the host, which suggests external origin, maybe through accretion of satellites, like I mentioned earlier. Another interesting corner is the bottom right here, where you have galaxies that are H1 poor, but are forming stars at a high rate. And this includes, for example, very exciting jellyfish galaxies, where the interaction with the intracluster medium as they fall into a cluster at high speed causes simultaneously the fast removal of H1, but also its fast conversion into molecular gas, and so a temporary enhancement of the star formation rate. Now, most of what I said so far is about relatively large galaxies, but H1 has been very important also to study dwarf galaxies. Through H1 observations, we've seen that dwarfs have very thick disks compared to their diameter, disks where the gas density is very low, and where the gas is rotating following a solid body or near solid body rotation curve, which implies very low shear. And all of these properties together mean that the effect of feedback from star formation is very strong on dwarfs and extremely long-lasting because of the low shear, and, for example, can explain the presence of these giant H1 holes in dwarf galaxies. Now, dwarf galaxies are very small, so easily perturbed, and you see a beautiful effect of this in this work by Mary Putman, where she analyzed a compilation of about 100 dwarf galaxies in the proximity of the Milky Way and Andromeda. You see here the H1 mass on the vertical axis. And here you see that essentially all the galaxies, all the dwarfs closer than 250 kiloparsec from the Milky Way or Andromeda have no H1 at all. They've all been stripped of their H1. In this case, the idea is through an interaction, hydrodynamical interaction, with the hot coronae around these galaxies. Another way of studying what happens to dwarfs around massive galaxies, but also in denser environments, in groups and clusters, is to study the H1 mass function, which at the low mass end is dominated by dwarf. And I'll go very quickly through this, but there is essentially growing consensus that the H1 mass function becomes flatter in denser environments because dwarf galaxies are essentially losing their H1 very quickly, and so they drop off the number counts here. But you know, counting galaxies is great, but I think it's hard to beat these beautiful images of extended H1 disks and velocity fields probing deep into the regions where baryonic matter and Newtonian dynamics seem to have issues. And so these disks seem to continue really to surprise us because they follow extremely tight structural and dynamical scaling relations. Here you see a relation between the H1 mass and the H1 diameter, which holds over 5 orders of magnitude in H1 mass with a scatter of just 15%, including the observational uncertainties. And we think that this is because of the very homogeneous surface brightness profiles of H1 disks. Another very interesting relation is a dynamical one between the radial acceleration you measure from the ISM kinematics on the vertical axis and the radial acceleration you expect just based on the distribution of baryons. And this relation is very tight. The shape of the relation is interesting, but what's amazing really is the scatter, again, just 15%, which implies a very tight coupling between the distribution of baryons and dark matter at sub-kiloparsec scale. Everything I've said so far, incredibly, is essentially at redshift 0, but we're now finally starting also to move towards higher redshift. This is showing work done with the GMRT by groups in India, showing the first statistical detection of H1 at a redshift of 1, stacking the H1 spectra of thousands of galaxies, essentially. And you see that statistically, the H1 mass is about a factor of 4 to 5 higher at redshift 1 than 0. And here you see the depletion time, however, being shorter because of the enhanced star formation rate. All right, that takes me to my final slide. I hope I've convinced you that H1 is a really critical stepping stone from the ionized gas in the intergalactic medium and the circumgalactic medium to the dense star-forming gas inside galaxies. It is also a great tracer of all kinds of interactions between galaxies and their environment, and a fantastic tracer of the distribution of matter through dynamical studies. And the final point is really that we are on an amazing, very steep curve of getting more and more H1 data from a range of telescopes. So there has never been, I think, a better time to engage with H1 astronomy. So, you know, jump on board. Thank you.
I like your delta star formation rate, delta H1 plot. And actually we know, as you showed size maturation, when gas is rich, most of H1 lying on the outskirts. Do you think that might suggest the radial inflow of gas from outer disk to inner disk is actually another way of gas accretion?
Yes, I agree with you. And in fact, may actually even have a slide about this. Yeah, here. In fact, I think that is being shown observationally. So this is work by Di Teodoro and Peak, where they analyze the radial inflows on H1 disks, on the disks of star-forming galaxies. And they detect, as you see, some negative component here, so some radial inflows. But if you go through the numbers again, it's insufficient to justify, to sustain star formation. It's about 10-20% of the star formation rate, similar to the accretion rate you get through accretion of gas-rich satellites. So I think I agree with you, yes.
Sorry, this is not really my field, but I noticed the LMC SMC have H1 masses which align, and so they have quite high H1 mass, but they are really close satellites of Milky Way, right? Here in this plot.
Yeah, they are the most massive ones of the lot. So the idea is that they are they've been able to retain their H1 because of their mass, but in fact, if you look at them, they're not really retaining their H1 at all. They're being destroyed by the interaction. So very soon, they'll drop down
But
as
then
well.
in the next plot where you show the mass, H1 mass, they follow the relation. Sorry, maybe one more slide. Yeah, this one. So
Yeah.
they are kind of still in the relation. So it seems the interaction has not yet moved them from there.
Yeah, it is one interesting, so this relation is built using the total H1 mass on the horizontal axis and this H1 diameter, which is actually, as a precise definition, is defined at the radius where the H1 surface mass density is 1 solar mass per square parsec. But the H1 is continuous beyond that. Now it continues beyond that, and very often beyond that point, H1 starts doing funny things, tails, gas moving in and out, and that's certainly the case of the Magellanic Clouds. And I think it's still a bit of a mystery to me why a lot of galaxies, not only the Magellanic Clouds, but lots of galaxies that are interacting in various ways with their environment still fall onto the relation. I think more work needs to be done there.
Thanks.
Hi, thank you. What are the prospects, in the next several years or for future surveys? Could we look at some of these giant Lyman alpha nebula that are observed at high redshift around these very massive galaxies and try and observe them in H1 to look at the different phases that we see in these giant nebula?
So as I said, doing H1 at high redshift is still very challenging. These detections I showed here are for massive galaxies with lots of H1, and they're stacking the H1 spectra of thousands of them. So it depends on what you mean by high redshift, and I suspect it's way too high for this. So you're probably better off trying to detect H1 in absorption if you can, because that's kind of redshift independent than H1 in emission.
Would this be something that like SKA might be able to do when that comes? Yeah. Okay. Thank you.
Just a couple of things. I remind all the speakers to put their slides online. Those who will go to the tower tomorrow, they can take the tickets at the secretary. Please do so starting at 2 o'clock. From 2 o'clock on, you can pick up the tickets there. And the other thing is, there is a lift if somebody wants to go up for lunch. And the lift is, we have to go out here, go around, enter the museum and take the lift from there. And also that is the best way to visit the Museum of the Opera. So just go outside, right, and take it. Thanks. And thanks to all the speakers really of this fantastic morning.